Hello CSCW, I am Santawat Thanyadit. I am happy to present our research, XR Live Enhancing Asynchronous Shared Space Demonstration with Spatial-temporal Assistive toolset for effective learning in immersive virtual lab. I did this work when I was with the Hong Kong University of Science and Technology. Currently, I am at Durham University. First, I would like to introduce the motivation of our research. Commercial virtual labs are often designed as self-learning tools, with students typically learning through text-based or video training. However, this removes the instructor from the learning process, and the student cannot learn from the instructor demonstration. Furthermore, instructors cannot create their own lesson in the virtual lab, and they cannot change the lesson to suit their students. To address this problem, we create a recording system for the instructor to perform a demonstration in the virtual lab, which creates a record in the virtual lab as shown on the right here. Once the instructor created a record, the record can then be distributed to the student. The student also used a VR headset to view the record of the lab demonstration, and at the same time, the student can practice along with the instructor. Finally, the student performance are submitted back to the instructor for evaluation. This video is an excerpt from one of our study participants. You can see the participant watching the instructor recording and practice the virtual lab from the instructor demonstration. Our work is mostly associated with the remote guidance literature. Related work of remote guidance can be classified based on an adaptation of time-space metric proposed by Johansson, and this work focuses on shared space asynchronous learning. The most similar research to our work is theory VR, which also investigates learning via recording. Another work that is similar to our work is How et al. That explores shared space asynchronous tasks. The main difference between our work and the other is our work is focusing on learning from demonstration that also requires the student to practice along with the instructor. Of course, there are several work in various areas that we also built upon. Please see the related work section in our paper for the detail. From the literature, learning from recording demonstration can be quite challenging for the student as there are many factors that can increase the student's physical and mental load. For instance, the instructor cannot provide real-time feedback or adjust the learning pace to fit the student performance like in real time. Furthermore, the students have to control the recording playback themselves, but since they are learning, they cannot predict what will happen. They also have to adjust their position to observe the demonstration. However, since the instructor also moves around in the VR using teleportation technique, the student may take additional time to find the instructor. So the research goal of this work is to investigate how remote students learn from an instructor recording in a virtual lab and design an assistive toolset to improve student performance. To complete this research goal, we perform two user studies. We perform a requirement study to determine the best demonstration technique in the VR lab and gather design requirements. We then create the assistive toolset based on these requirements and validate them in the validation study. In both of our user study, we chose the unconfined compression test as the topic for our virtual lab demonstration because this is a standard lab for civil engineers, and because it characterizes conventional science and practical engineer lab. It has 14 steps as shown in this slide. We examined three traditional virtual lab demonstration techniques in the requirement study. Video, which has the instructor perform a demonstration in the 2D video similar to the current commercial virtual lab. Avatar, which has the instructor share the space with the student similar to the real lab. And Shadow, which has a semi-transparent instructor that students have to align themselves with to perform the task. The requirement study showed 4 participant behavior that could be used as design requirements. First, we observed that the participant didn't know when to stop the record and tend to learn too many steps between pause, which make them more likely to make mistakes while practicing the task. To encourage step-by-step learning, we built the auto pause and checkpoint feature. I will discuss this later in detail. Second, in terms of cooperation with the instructor, the participant rate the avatar condition as the best since it resembles the practical lab experience. As a result, we use the avatar condition set up as a basic demonstration technique. Third, we found that participants had to shift their attention to the instructor workspace, which may lead to more mental effort. However, the shadow condition did not have this problem since the participant and the instructor share a single working space. So we utilize visual cue from the shadow condition by superimposing the instructor's semi-transparent workspace over the student workspace to help the student better copy the action and compare their progress. Fourth, we noticed that the participant tried to keep the instructor in their view by keeping a distance from the virtual instructor. However, if the students are too far away, they may miss part of the demonstration. So we replaced the teleportation in the recording with a walking animation as shown in this slide and add text panel to increase student awareness. To address requirement 1, we add an auto pause and checklist feature. When the playback lists the checklist, the playback stops automatically for the student. This lets them know it's time to start practicing the task. The student can only view the next step after they complete the task and check the item on the checklist. We also built a save and load feature to make it simpler for students to correct their mistake. These features are grouped into temporal assistive toolset. As previously mentioned, we addressed requirements 3 and 4 by utilizing visual cue from the shadow condition and replacing the teleportation in the recording with a walking animation to increase student awareness. These features are grouped into Spatial-assistive toolset. We conduct a validation study with 24 participants to compare learning in the virtual lab between 4 conditions: avatar only without any tool, temporal tool only, spatial tool only, and a condition with both type of tool enabled called Spatial-temporal toolset. We compare these two to figure out what effect each feature has on how students act and compare them. During our study, we asked the participants to learn the lab procedure from the recording and then perform the lab procedure on their own as a test. We test once right after the learning and once a week after to test a memory retention. We found that participants who use both of the assistive toolset outperform other conditions in terms of score and memory retention, as you can see from this graph. The self-assessment questionnaire also showed that participants with spatial-temporal toolset report better attention allocation and a sense of co-presence with the instructor. This showed that the proposed assistive toolset help manage student attention. We also observe other important student behavior. For instance, students cannot accomplish simple tasks quickly in the virtual world. As you can see, this participant has to adjust his position multiple times and sometimes struggle at simple tasks like grabbing the virtual objects because there is no physical feedback. During this time, this participant already missed some lab procedure because he was trying to perform the task in parallel with the instructor. To make matters worse, the student rarely rewind the record to check for mistakes. As you can see from this event graph, the number of seed control is significantly less than other types of control input. All these observations further highlight the importance of proper learning step design and the guidance of student attention. We also discuss future improved design in our paper, so please see our paper for further details. Our contribution can be summarized into 4 points in this slide. Thank you very much for your attention. I am happy to answer your question now.